The discovery of neuropod cells has opened a striking new frontier in our understanding of appetite control, one that could shift how we approach overeating and metabolic diseases. These specialized gut sensory cells, which combine features of neurons and hormone-secreting cells, form a rapid communication network between the gut and the brain. Unlike traditional hormonal satiety signals that take minutes to circulate, neuropods transmit information about what we eat in real time, within milliseconds, via synapses connected to the vagus nerve. This speed and specificity raise a compelling question. Could we harness neuropods to help people feel full sooner and naturally regulate food intake? In contrast to slower hormonal regulators like leptin or insulin, neuropods respond directly to nutrients, glucose, amino acids, fats, by sending fast electrical signals to the brainstem. These signals don't just say calories incoming. They carry detailed information about food quality, nutrient type, and energy density. From there, this information is integrated in the brain's appetite centers, such as the nucleus tractus solitarius, NTS, and hypothalamus, to influence decisions around continuing to eat or stopping. The fact that these signals precede conscious awareness makes neuropods particularly attractive targets for modulating eating behavior below the level of willpower or restraint. One of the most intriguing clinical implications is for treating obesity and overeating without drugs that suppress appetite bluntly. Instead of manipulating hunger artificially, targeting neuropods could enhance the body's natural satiety pathways, reinforcing the "you've had enough" signal at the exact moment it's most biologically appropriate. For example, researchers have already shown that stimulating neuropod activity in mice reduces food intake by boosting vagus nerve activity and increasing feelings of fullness. If this can be safely replicated in humans via nutritional compounds, probiotics, or gentle electrical stimulation, it could represent a next-generation tool for weight management. Diet plays a key role in this, since neuropods are influenced by what types of nutrients and microbial metabolites they encounter. Processed foods, which are engineered to be rapidly digested and absorbed, may fail to adequately activate neuropods, depriving the brain of timely satiety signals. On the other hand, high-fiber, whole foods lead to slower digestion and greater fermentation by gut bacteria, producing short-chain fatty acids like butyrate and propionate, which are known to activate gut sensory pathways and promote fullness. This may explain why whole food diets are more satiating calorie for calorie than ultra-processed diets. In addition to nutrient sensing, neuropods also respond to microbial signals, meaning that our gut bacteria may help shape how these cells function. Certain probiotics, like Lactobacillus rhamnosus or Bifidobacterium infantis, have been shown to interact with enteroendocrine cells and influence vagal tone. If specific strains can enhance neuropod function or make the gut-brain satiety loop more efficient, they could serve as microbial boosters of fullness, reducing the need for caloric overcompensation. This is particularly exciting because it suggests a long-term, side-effect-free method to support portion control by improving internal feedback, not external restriction. Even more innovative are the possibilities of neuropod-targeted therapies that use light or electrical impulses to trigger these cells directly. Research teams have already developed optogenetic tools to activate neuropods with high precision, demonstrating measurable reductions in food intake. In a clinical setting, future devices could use similar principles, perhaps through a smart ingestible capsule or gut-targeted neuromodulation patch, to help regulate appetite in real time, with minimal invasiveness. The implications extend beyond weight loss. Enhancing neuropod activity could improve glucose regulation, since these cells help signal carbohydrate presence and prompt insulin-related responses. They could also assist in correcting disordered eating patterns where the internal signals for hunger and satiety are muted or misinterpreted, such as in binge eating disorder or night eating syndrome. Restoring the precision of gut-to-brain communication may be key to re-establishing trust in bodily cues. Of course, there are challenges. Neuropods are scattered throughout the gut and relatively few in number, making them hard to study or manipulate without affecting other systems. Individual variability in gut anatomy, microbiota composition, and vagal nerve sensitivity means that not all people would respond the same way to neuropod-based interventions. And ethical considerations arise around using technology to intervene in a deeply personal behavior like eating. Still, the science of satiety is evolving rapidly, and neuropods represent the most targeted, biologically aligned way yet to help the body recognize when it's had enough. They offer a way out of the willpower trap, not by dulling appetite or punishing overindulgence, but by amplifying the body's original design for energy balance. If developed with care, neuropod-based therapies could redefine what it means to eat intuitively, helping millions regain control over their appetites by simply letting the gut's quiet intelligence speak more clearly to the brain.